Hello everyone, and I'm going to talk about the stochastic mode reduction. Actually not the whole project. I did this project with Mukesh and Sandeep. So they will talk about the stochastic mode. Mukesh will talk about the stochastic mode reduction part, and Sandeep will talk about the model which we have considered. And I will talk about, so this is the outline of my talk. I will be sprinting through this 5 slides. I'm going to talk about this averaging and homogenization, and then Mukesh will talk about the shallow water waves, and then from shallow water waves to quasi-geostrophic waves, and then Mukesh will talk about the stochastic mode reduction, the problem which we have considered. Now, well, while doing the various climate model, we often come across some nonlinear stochastic partial differential equation, and how to deal with them, and how to make sense out of the various variables which we have. And these variables, they have different time scale evolution. One variable could be very fast, and other variable could be very slow. So how to model such system in terms of a slow moving variable, or which is the result variable, and also consider the contribution by the unresolved variable. So that is mainly done by this averaging and homogenization. So we will consider one equation, and so equation 1, it represents the it is an advection diffusion equation. It represents, for example, if you consider a ink in a water, then this T is the concentration field, V is the velocity field, D is the diffusion coefficient. So the right hand part of this equation, it represents the diffusion, and that part it represents the advection. And we will consider that, okay, the velocity, so we will consider few cases. So here, first case, we will see that if the velocity is smooth and it is steady, velocity field is smooth, it's steady, and it's periodic, then we can write this velocity field as like this, B of x, and then we will say the fluid is incompressible fluid. So we can say that. And then taking the initial condition, now here is the gist that when we take this initial condition where T0 is the concentration and T0 is expressed in terms of some function g, which is the function of x, but that x is scaled by epsilon, and that epsilon is very small than 1. So that means the T0, that is initial concentration, is varying over a large scale of time and over a large scale of space. So we will scale our x and t by this scale. We will do this rescaling of x and t, and then our advection diffusion equation becomes like that. In case, so now here also we will consider few scenarios, like if diffusion is very small. Diffusion is 0, there is no diffusion, and A is 1, that scaling factor, we will take A is 1, and then using the method of characteristics, one gets this equation where this epsilon is not raised to epsilon, but it represents that x is scaled by epsilon, so that is scaled x, which is scaled by epsilon. So now here in this equation we see that B is periodic, and this function is scaled by epsilon, and it varies rapidly. So the point is, when we find a scale difference in some stochastic partial differential equation, it is intimately related to the averaging of ordinary differential equation. So the best way is either we can take average, or if the variation is over larger scale of time, we can go for the homogenization. So so if diffusion is greater than 0, we have some diffusion, and A is 2, we get this backward Kolmogorov equation, again following the same thing as we did in this equation. So from this coupled partial differential equation, we end up to this ordinary differential equation, which is nothing but the backward Kolmogorov equation, where D is the diffusion constant and this W is the standard Brownian motion with its mean is 0 and time correlation function, it's delta time correlation function. So, after eliminating the rapidly varying quantities for periodic and divergence-free zero mean field velocity, we get this equation. Da by x by da by t is this where x is to epsilon converges to xt, as we say that the epsilon tends to 0. And here this kappa is nothing but the coefficient of diffusion, and this W is nothing but the Brownian motion. So I will come to the last part of my presentation. From here, Mukesh will take over. That averaging versus homogenization. So now the basic principle underlying behind this technique is nothing but the formal perturbation expansion of the linear operator. So if you consider over a larger time scale, you will go for the homogenization, which is this, and where you expand the operator in terms of this, where epsilon is the scaling coefficient, scaling factor, not coefficient, scaling factor. And when you go for averaging, you will end up with this linear operator. And so this is the averaging and homogenization part. So from here, Sandeep will talk about what system we have taken. He will talk about how from shallow water we have arrived to quasi-geostrophic, and then which system we have modeled, and then Mukesh will talk about the stochastic mode reduction.